Hey everyone, welcome back to my channel. So I have posted 6 lectures regarding the redox reaction, and there I have explained few examples showing the calculation of oxidation state. I hope you have gone through them. If not, please go through my previous video. I have brought few more examples for you so that you get to know more techniques to solve the oxidation state. The first example for today's class is C3O2, which is called carbon suboxide. This is also called carbon suboxide. And here you are asked to calculate the oxidation state of carbon. That means we will consider the oxidation state of carbon as X. So how to do it? So first of all, 3x, because we are having 3 carbon atoms, so 3x plus, the name itself suggests oxide, so it is minus 2 into 2. Let's see whether this oxidation state is possible or not. If not possible, we will consider the peroxide bond. So 3x plus minus 2 into 2, that means 3x minus 4 is equal to 0. So x comes to be plus 4 by 3. Plus 4 by 3, which is definitely possible. Carbon atom can have oxidation state up to plus 4. The oxidation state of carbon can be up to plus 4 depending on the electronic configuration. So carbon has atomic number 6. Its electronic configuration is something like this: 1s2, 2s2, 2p2. That means a maximum of 4 electron loss is possible. That means maximum oxidation state of carbon can be plus 4, not more than plus 4. It can be less than plus 4 but not more than that. So here the oxidation state of carbon comes to be plus 4 by 3. As I have already explained during the differences between valency and oxidation state, I have already told you that it is possible that some elements have oxidation state in fraction or in decimal. So here you are finding that the oxidation state of carbon is plus 4 by 3. Now let's see how is the structure. The structure is something like this. This is the structure of carbon suboxide. Now remember, whenever you find this kind of moiety, this kind of thing, carbon, 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 double bond. Whenever you find this kind of moiety or this kind of linkage, this kind of bond, moiety or bond, whenever you find this kind of bond, remember this is called alene bond. Alene. Carbon, double bond, carbon, double bond, carbon. This is called alene bond. So here what does this suggest? That the middle carbon atom, let me take a different color so that it is easy for you to understand. The middle carbon, which has been taken to be brown, the middle carbon atom, if you see, I have told you that in heteroatomic molecules or in heteroatomic bonds, when an atom is bonded to similar type of atom, if you see clearly that the brown carbon atom is bonded to 2 other carbon atoms. On the left hand side it is having a carbon atom. On the right hand side also it is having a carbon atom. That means the brown carbon atom is surrounded by 2 carbon atoms as well. So oxidation state of the brown carbon atom is considered to be 0. The oxidation state of brown carbon atom is 0 because in heteroatomic bonds, in homoatomic bonds, that means atoms bonded to similar type of atoms. In homoatomic bonds, the oxidation state is 0. Here the brown carbon atom is surrounded by 2 other carbon atoms, is bonded to 2 other carbon atoms. So the oxidation state of carbon is 0. What about the other 2? The other 2 should be plus 2. Remember, there are 3 carbon atoms. X is the average oxidation state. This is the average oxidation state, because all the carbon atoms are not same. One carbon atom is having a 0 oxidation state, whereas the other 2 carbon atoms are having +2 oxidation state. The black carbon atoms have a similar environment, both bonded to oxygen atoms. But the brown carbon atom in the center is surrounded by 2 other carbon atoms. It is bonded by homoatomic bond. The brown carbon atom is surrounded by homoatomic bond, which means that the brown carbon atom will have a 0 oxidation state, whereas the other 2 carbon atoms will have a +2, which means if you see, the average oxidation state comes out to be, average oxidation state comes out to be +2 +0 +2 divided by 3, because we are having 3 carbon atoms. So it is 4/3 +4/3. The oxidation state of the carbon atom, whichever is shown here, +4/3, that is the average. If you find out for individual carbon atoms, the middle carbon atom shown with brown color is having a 0 oxidation state, whereas the other 2 is having +2 oxidation state. Now let's move to another example of a similar type so that it is easy for you to understand. Let's take the example of sodium tetrathionate. Sodium tetrathionate, the formula being Na2S4O6. The name of this compound is sodium tetrathionate. The name of this compound is sodium tetrathionate. Let's see what to do. We are asked to calculate the oxidation state of sulfur. Let us consider that to be X. So +1 into 2, because we know sodium can have only one type of oxidation state. Being a representative element, being a S block element, representative element, it has only one type of valency or one type of oxidation state. You have learned in your junior classes that the transition metals, the D block elements, have variable oxidation state, but the alkali metals, the representative elements, can have only one type of oxidation state. It is +1 into 2. Plus sulfur, let's consider that to be X, 4 into X, because we are having 4 sulfur atoms, plus oxygen. Let us take it to be oxide first. If not, we will go for something else. -2 into 6 is equal to 0. That means it comes to be +2 plus 4x minus 12 is equal to 0. So it is 4x minus 10 is equal to 0. So x comes to be 10/4. 10/4, or we can also say it is 2.5 plus 2.5. The oxidation state of sulfur in sodium tetrathionate is +2.5. I hope you remember, I have told you that the maximum oxidation state for sulfur is +6. Beyond +6 is not possible. Below +6 it is possible. It is +2.5, so it is definitely possible. Now here let's see the structure. As we have got the oxidation state in decimals, we need to know the structure. It is something like this. We have 4 sulfur atoms. I have already said you cannot change the molecular formula. The structure is somewhat like this. The structure of sodium tetrathionate. Sodium tetrathionate. Sodium tetrathionate. This is the structure of sodium tetrathionate. What can you see from here? That we are having 2 sulfur atoms in the heteroatomic, in the homoatomic bond. 2 sulfur atoms. If we take that for a different color, then it will be clear for you. Let's take a different color. the middle brown carbon atoms, 2 carbon atoms I have shown in brown. See, they are in a homoatomic bonded state. Homoatomic bonded state, because both the brown carbon atoms are bonded to sulfur atoms. So it is homoatomic bonded state. So that means the oxidation state of the brown carbon atoms will be definitely 0. Will definitely be 0. So the other two will have a different. The other two will have a different one. I hope it is understood to you. So that means the other two sulfur atoms will have a +5 oxidation state. +5, which is possible. The other two sulfur atoms will have a +5 oxidation state. Let's see how. That means +5, the first sulfur atom, +5, +0, +0, +5. We are having 4 sulfur atoms, so divide by 4. Divide by 4, that means it is +10 by 4, that means +2.5. So the +2.5 is actually the average oxidation state. The +2.5 is the average oxidation state for sulfur. All the sulfur atoms do not have the same oxidation state. The brown sulfur atom, which are in the homoatomic bonded state, have 0 oxidation state, whereas the other two sulfur atoms have +5 oxidation state. Now the next question is when to understand, when to think in this way. Whenever you find that the oxidation state comes out in decimal, whenever the oxidation state comes out in decimal, in fraction, think that all the atoms may not be having the same oxidation state. As I have shown you for carbon suboxide, as I have shown you for sodium tetrathionate, all the carbon atoms were not same, and here all the sulfur atoms are not same. 2 sulfur atoms having 0 oxidation state. It is not possible to predict the oxidation state of all the sulfur atoms through the average oxidation state. The average oxidation state will give you as a overall, as a whole thing. So that is why, to know the individual oxidation state, which atom carries which oxidation state, you need to know the structure. Whenever the oxidation state comes out in fraction, you need to know the structure. Okay, let's move to another example. Say for example, if I take example of CrO2, Cl2, chromyl chloride. This is a very useful thing. You will when you do the practical for your qualitative analysis, that means cation anion detection. Qualitative analysis, when you do qualitative analysis for chloride ion detection, chloride ion detection, chromyl chloride is formed. Chromyl chloride, this is called chromyl chloride. Chromyl chloride is formed during the chloride ion detection. You will do that in your practical classes. Now the next one is, if you are asked to calculate the oxidation state of chromium in chromyl chloride. Next, let's take this as X. Let's consider that the oxidation state of chromium is X. So it is X into 1, because we are having only one chromium atom, plus let's take oxygen as -2 first. If it is not within the range, we will consider something else. So -2 into 2, always start with oxide consideration. If it is not within the range, we will move to the next peroxo bond. Plus chloride, chromyl chloride means it is -1 into 2. Chloride means it is -1, right? And is equal to 0. So X -4 -2 is equal to 0. X is equal to +6. You have already seen in the previous video. If not, please go through that. I have already shown you that the maximum oxidation state possible for chromium is +6. Chromium is a transition element, it is a D block element. It can have variable oxidation states. It shows multiple oxidation states, +2, +4, +6. Similarly, +6 is the highest. It cannot have more than that. So in this compound, chromyl chloride, the oxidation state of chromium comes to be +6, which is possible. Now let's move to another example. Say if I consider the oxidation state of sulfur in sodium thiosulfate, Na2S2O3, sodium thiosulfate. The name of this compound is sodium thiosulfate. You are asked to calculate the oxidation state of sulfur in sodium thiosulfate. Let's consider sulfur as X. So +1 into 2, the oxidation state possible for sodium is +1, plus 2 into X. Let's take as oxide first. -2 into 3 is equal to 0. Let's check whether the oxidation state is within the range of sulfur. +2 plus 2x minus 6 is equal to 0. So 2x minus 4 is equal to 0. So x comes to be +2, which is possible. That means, as we know, the maximum oxidation state possible for sulfur is +6. In sodium thiosulfate, it comes to be +2, which is possible. In sodium thiosulfate, the oxidation state of sulfur is +2. It is not in decimal. It is a simple whole number. It is not a decimal, not a fraction. So obviously both the sulfur atoms have equal oxidation state. Now let's move to another example. Each sulfur atom is having +2 oxidation state. Each sulfur atom is having a +2 oxidation state in sodium thiosulfate. Let's take another example. Say H4P2O5. H4P2O5. The name of this compound is pyrophosphorus acid. There are many oxy acids of phosphorus. You have seen for sulfur as well. Sulfuric acid, sulfurous acid, Marshall's acid, Caro's acid. You have seen many oxy acids of sulfur. Similarly, pyrophosphorus acid is another oxy acid of phosphorus. Phosphoric acid, phosphorus acid and pyrophosphorus acid. These are the oxy acids of phosphorus. Many more are also possible. Now we are asked to calculate the oxidation state of phosphorus here. So let's take X. So +1 into 4. Since hydrogen is bonded to more non-metallic, both phosphorus and oxygen are more non-metallic than hydrogen. So it is +1. +1 into 4 plus 2x and oxygen to be -2 into 5 is equal to 0. Let's take as -2 first. If it is not within the range, we will go for something else. Now +4 plus 2x minus 10 is equal to 0. That means 2x is equal to 6. 2x is equal to 6. So x comes to be +3, which is within the range. The maximum oxidation state possible for phosphorus is +5. Why is it so? KLM 285. If you remove these 5 electrons, then what happens? It gets a noble gas configuration. That means a maximum of 5 electron loss is possible. So +3 is within the range. So the oxidation state of phosphorus in pyrophosphorus acid is +3. Now let's take another example. Say if I choose an oxy acid of chlorine, say for example HClO4. HClO4. In your junior classes you have only learned about HCl, hydrochloric acid. Chlorine can also form oxy acids, HClO4, then HClO3, then HClO. All these are various oxy acids of chlorine. Similarly, bromine and iodine, chlorine, bromine and iodine can form oxy acids. If needed, I will make a separate video for oxy acids. What are oxy acids and how to identify them. After that, only fluorine cannot form oxy acid. Why is it so? Because fluorine is a very small element. It has only 2 shells. It lies in the second period of the periodic table, right? Fluorine is 1s2, 2s2, 2p5. That means it has only 2 shells. It lies in the second period. As it can form only one oxidation state, fluorine can have only -1 oxidation state. So that is why fluorine cannot form oxy acids. Let's see, for example, if I want to show you the oxidation state of chlorine in HClO4. So what happens? It is +1 into 1 plus chlorine. Chlorine is X into 1. Why did I take hydrogen to be +1? I hope you know it, because hydrogen is less electronegative than both chlorine and oxygen. Now the next one is oxygen. Let's take as -2 first. -2 into 4 is equal to 0. So it is +1 plus X minus 8 is equal to 0. So X comes to be +7. Is it possible? Let's check. If not possible, we have to go for something else. The electronic configuration, the atomic number of chlorine is 17. So the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p5. 3s2, 3p5. Or if I show you the simple one, it is 287. 287. If you remove these 7 electrons, from chlorine, 7 electrons are lost from chlorine. Then what happens? It achieves a noble gas configuration 2,8. Chlorine plus 7 gets a 2,8 noble gas configuration. Though I am explaining with respect to electron loss, the correct explanation is actually for variable covalency. I will take a separate class for that. You will understand. When I teach you chemical bonding, you will understand. So due to variable covalency, chlorine can have a maximum of +7 oxidation state. That means this +7 oxidation state is definitely possible for chlorine. So I end my lecture showing the calculation of oxidation states. If you want me to solve more examples, you can write on the comment section. I will go through that. I will take a separate class for that. In my next class, I will teach you how to balance chemical reactions using ion electron method. Please stay tuned for that. My class will be very helpful for you all. Thank you.